All right, do we have Glenn there? Oh no. Welcome everyone to our Learn Live session. And right here off the bat, we seem to have some internet issues, I think.
No, it's all good, Jason. I'm here.
Oh, you are there. All right. Welcome everyone. I'm going to let Glenn take over here.
No worries. Welcome everyone to another Learn Live session. Good morning, good afternoon, good evening, wherever you are on the planet. It's great to have you joining in. Use the chat window. Let us know where you're joining in from. We're excited to have so many people here. What is the first of a 9-part series on machine learning? In today's session, we're looking at an introduction to machine learning. Jason's going to take you through what some of the other courses are as well a little bit later. My name is Glenn Stevens. I'm a senior content developer here on the Learn Live team. I'm here with my good friend and colleague, Jason DeBoever. Jason, do you want to introduce yourself to the world?
Hi, yeah, I'm a senior product manager here at Microsoft. Specifically, I work on the ML and AI content for our docs.microsoft.com site, including some of the docs and, of course, the Learn content. In fact, I kind of acted as the, I guess you could say, executive producer of this learning material that you're going to see here. Worked with some amazing authors who did the real hard work and heavy lifting of creating all of the labs, exercises, code, and of course the content that we're going to go through today.
Excellent. And I can see on the PowerPoint slide that we've actually got a link to today's session, right? The aka.ms.learnml. You can actually go there and look at the whole series that we're working with today. And this is just the first of the 5 sessions that you can see on the screen. There's actually aka.ms/learnml-introduction. That's today's session. That's the one we're doing, which is Introduction to Machine Learning, that first in the list of 5 that you can see on the screen. And we're doing a range of others as well. We're building classical machine models. We're looking at Introduction to Data for Machine Learning, how to work and manipulate with data, looking at things like how to train and understand regression models, refine and test those regression models, and a range of other things too, things like classification models, architectures and hyperparameters, confusion matrices, optimizers, all this fun stuff. It does sound a little bit complex, but we'll actually take you along a smooth path and explain it along the way. It's very exciting.
Yeah, we've got 2 months to go through it. We're going to be doing 9 sessions over the course of the next 2 months. So we've got a good amount of time to get all of this material into your brains, and we'll work on doing exactly that. So as Glenn mentioned, we've got our aka.ms link for today's session. Glenn, you want to tell them what to expect out of that?
Well, you can expect really a few things. We're going to take you through the process of what's a machine learning model, how to create one, create a very simple one for today's one. It is a very gentle introduction, and we'll show you how to use it, how to work with data a little using a framework called Pandas, which is really quite common and popular, and essentially simulate what's going to be a little website. And we'll talk about that in a few minutes. And if we just move on to the next part, I do want to mention we are live and interactive. I'm wondering where everyone's connecting in from. Hopefully we've got a few people connecting in on the chat. It is on chat. We are live. We can hear by the first mistake at the start with the unmuting. But Jason, any other comments?
No, it's like you said, we are live, and we are on opposite sides of the planet, by the way, Glenn and I. So Glenn is over there in Australia. I'm here in the US, in Michigan specifically. So we're on opposite sides of the planet. That means, you know, we might expect some lag here and there. So if you're experiencing that, if you see that there's a little bit of lag, then understand that even in today's day of giant undersea cables, we occasionally get some intercontinental lag.
Yeah, but I can see we've also got some people on the chat from Costa Rica, Argentina, Quebec, Chicago, Nigeria. There's a huge range of people. Awesome.
Outstanding. That's great. Yeah, from all over the place. I love that. Everywhere from where we are and everything in between, right?
Right. So we've got some moderators that are helping us out today, Jason. You want to speak to that?
Yeah, so these are just some amazingly talented subject matter experts who are going to be working in our chat channels. So if you're in chat right now and you have a question over the material that we're going over, again, we're live. We're going to be able to help you real time with some of your questions. Of course, keep it on topic. We are not going to be able to answer every machine learning question that ever comes up. Although, give it a try. So our subject matter experts in the chat window just might be able to help, because these people are really knowledgeable. And occasionally they'll throw one of your questions up to us, and Glenn and I will field it as well.
Awesome. All right, so let's get into today's content. All right, over to you, Jason.
Yeah, so what we're going to be dealing with today is a very, very high level introduction to what is machine learning. So we're going to be talking about that today. And in fact, we'll even still stick with a pretty high level overview in our next session. That episode 2 will still stay fairly high level, still kind of a survey of everything, but just drilling down a little deeper. After that, our sessions after that will actually start digging deep into some of the vertical aspects, certain types of machine learning, and certain things that we need to do as part of our machine learning process. So today, we're going to address what are machine learning models. And that's the very first thing we're talking about right here with this slide. So a machine learning model, in many ways, is like a function that you would code if you were writing code. Now, I'm going to speak to coders somewhat because I think that's a fair amount of our audience. If you don't have experience coding, don't worry, it's not required for this actual session, for this conversation. But because I think that's a fair amount of our audience, I'll occasionally direct some comments at coders. And so a machine learning model in many ways does act like a function. You get inputs and you expect an output. The key difference is that with a machine learning model, we're going to use data to help decide what that function should do. A common example, and one of the early practical machine learning models, were spam filters. Now, early spam filters, they did try to do things with imperative code, like identify words that are just always spam emails. But those models didn't work nearly as well as some of the very early machine learning models. Those functions, those imperative functions, didn't work nearly as well, because what they were able to do with these early machine learning spam filters was look at all of the emails that we all get every day. They were able to look at all of those emails and see which ones we're flagging as spam. And so by knowing that we humans flagged all these emails as spam, and then all these other ones that we didn't flag as spam, we were able to feed that into some machine learning models, and we'll start to understand what that's about in a few minutes, and get a better function than anyone could hand code at the time, and probably still today.
That's true. One of the nice things about spam filters, Jason, is that as you get more data, as you get more emails and you train it more and more, it actually gets better and better, right?
Absolutely right. And so when you go in, even though our spam filter does try to spam filter things, if we actually go in and say, oh, that's not spam, we're helping to improve those algorithms. And same thing, of course, when we continue to add more spam to our list of things that we don't want. So we've got a scenario that we're going to be working through today as part of our example. It's not a spam scenario. Do you want to tell us about that?
Sure. It's just as useful. This is a business that sells harnesses for Avalanche rescue dogs. And essentially what the business has found out is that people are buying the harnesses for these rescue dogs and also buying the boots, but the boots are actually the wrong size. But the business knows that if you're buying a harness size of a particular size, the boot size should actually kind of match in some way. They don't quite know the formula, but they want to use the data in order to work out what that value should be, or at least the range roughly of what those values should be, with a little bit of domain knowledge. So what we're going to do is we're going to look at the data for the harness size, for the boot size, and see if we can come up with a model, a machine learning model, that actually represents that business rule for them. And we could do things like we could warn the customers, and we'll see that a little bit later towards the end of today's session.
Yeah, see what we can actually do with our business once we have these models to use. How can that help our business?
Yeah, but we've talked about models a fair bit, but why don't we go through probably a more in-depth definition of what's a machine learning model?
Yeah, we don't want to get too in depth yet, but certainly we're going to take another pass, and in fact, we'll of course keep doing that. Keep taking additional passes and getting deeper and deeper over the next 9 episodes. But But we already sort of answered the question, what are machine learning models? They're functions that we create from data. But how do we get there? What do we do? What data are we using? And the answer is that our model is that core function, but we need a process to turn that basically a wireframe of a model, I'll say, an incomplete model or a model architecture. We'll start with that. And that's something that we will choose as the ML engineer or the ML implementer, the ML practitioner. We will choose this starting type of model, but it's incomplete. We need to feed it data. And then once we feed it the data, our process, our training process, can start to figure out how to complete the model for us. Now, models can be very, 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 very simple, or they can be very, very, very complex. Now, I'm going to show you an example of an absurdly simple model here. So this absurdly simple model here has an input, a single multiplier, a single multiplication parameter, and then some expected output. So if we look at the scenario, Glenn, this matches the scenario you mentioned earlier, right?
Yeah, that's right. We've got the harness size, but we want to know what the boot size is. I can see a parameter here that we like multiply it by 2.5. That seems very rough, but it may not always fit every particular situation, right?
Exactly. So if we start with this very simple model, surely with one data point, we can fit it and say, all right, yep, if we just have this model that is just multiplying by one number, yep, we can fit this one data point, multiply by 2.5, and the math works out. However, this is not going to generalize. If I start looking at more of my rows of historic data, I'm going to realize that this isn't a very good model at all. Right. And so that's what we want is a model that can generalize. So this one is probably too simple. It's probably not going to generalize. Now, a model that's not much more complicated, however, is actually useful in many real world situations is the one that we see on screen now. So now we've just added one additional parameter, but this actually has an interesting property. Glenn, does this look familiar? The numbers and the math on screen?
Yeah, when I saw this the first time, I went, oh, this looks like my high school maths, where it was the y equals mx plus b, where you're drawing the trend line between a bunch of points, right?
It's exactly what it is, right? So this is plotting a trend line. And we could say, all right, for our harness, when we go across kind of, let me get my laser pointer here. If I'm going across the bottom of a graph, right, and mapping harness size 1, 2, 3, 4, then I can actually see that I'd have another axis there for the up and down for the boot size, and our parameters here basically can create a trend line. And we're going to see this in our first lab, our first coding exercise. We're going to actually see that trend line and see how that gets us a very, very good model, even though it's not super simple, or it is fairly simple math. It's just a single multiplication and a single addition to get there. Now, finding what the right things to multiply and add by, well, that's not necessarily so simple. It will be definitely achievable and approachable for us, but it definitely requires some explanation. And don't worry, we're getting there. We start by just picking something. Once we've selected our basic model, in this case, the basic model we're selecting is that trend line, and it's sometimes called linear regression or ordinary least squares. But the idea is we're just trying to get a trend line, a single trend line from a single input of data. In this case, actually the linear regression ordinary least squares model can generalize to many more inputs, and we actually do see that in some of our later episodes. And not even that much later. I think episode 3, maybe 4, we'll actually start working with those. So here we start with just any parameter value. And the reason it's just any is because we have a training process with machine learning. We are going to start with just some value. Then we're going to feed a lot of that data into our training process, and it's going to start changing the parameters for us. And we can see when we start with our random numbers, it's not very good. I think this equals 2, right? So that didn't work. But our training process, and we'll talk about how that works in just a few minutes, our training process is able to realize that those parameters are way too small and start eking those numbers up bit by bit by bit until it's unable to further improve, until it's gotten as good as it can get.
Yeah, it's interesting though. I think in our case here, we're trying to look for the answer with something like a trend line to find the most least incorrect value. Would that be a fair assessment?
That's a great way to put it, because what we'll see once we start playing with that data is that our real world data that we're using for training, it isn't going to perfectly match the trend line. It's going to be kind of rough and all over the place, but we'll see that the trend line is a good general match for our historic data, and therefore will be a good rough suggestion for our future boot sizes. You know, there's a couple things to really notice here, and that is that even though I've selected a very simple model here, it should drive home the point that all of our machine learning is just mathematical transformations. Even our most complex models are just mathematical transformations. There's just more of these parameters, sometimes billions of them, in fact, as it turns out with some of those things that we see about in social media doing crazy stuff. So there can be billions of parameters, but it's still essentially mathematical transformations of the inputs. And you can have more inputs as well. And sometimes even turning your inputs into numeric representations, like if you have a text input. Well, there's some tricks to turning that into numeric representation that happens even before you get to training your model. But you get that numeric representation, and then the training of your model and the actual machine learning part is just finding those optimal parameter values. And it's just that application of multiplication, division, those sorts of things, mathematical transformations.
Right. So we do have a demo. It should be a little bit of fun. We've been talking about all this theory. Let's put it into a little bit of practice. And in our session, we're going to look at how we can prepare some simple data, how we can select a model, a very simple model, the one that we've been talking about so far. We'll look at training and then also using this model and to kind of estimate a value. It should be a lot of fun. Let me just share my screen. Yeah, we'll switch over here. And I'm actually running in the Microsoft Learn environment here. One of the nice things we have with this particular series is that it's using Jupyter notebooks, which means we can actually execute all this in the browser. You don't need to set up any infrastructure. You don't need to run anything else. It's all in the browser. As long as you've got a Microsoft ID and you're logged in, you can execute on the sandbox.
Glenn, we're not seeing your screen actually, and for me at least, your video is a little jittery. So those undersea cables are of course wreaking havoc with a live demo, because that's how they do.
They may do. Let me see if I can correct this. Do you want to share the screen back again, Jason?
Yeah.
How live are we right now? We are so live.
There we go. We are so live right now.
All right. I may just have to switch networks, unfortunately. Yeah, so we have this preparation of data. We'll select the model. I'll just switch over very quickly.
And I've got that sandbox environment up too. So if we need me to drive, no problem. All right. I think we might be going that route.
No, I'm just sharing my screen now. Hopefully you can see that. Is it all visible on the screen for you now, Jason?
Well, sort of. It's not good enough, I'll say that. We've got a lot of pixels.
Well, you might. Well, why don't you host it for us, and we'll run through it.
You got it. Here we go. Like Glenn said, we're so live right now. Did this ever happen in rehearsals? No, it did not.
No. So you can see on Jason's screen here, we have the training and running your first model. And that's really what we call a cell in Jupyter Notebooks, if you've not used Jupyter Notebooks before. And it really is just a list of descriptions, and also a list of executable cells underneath. So we've got some descriptions here about what we're going to do. We're going to train and run our first model. We're going to go through that process of looking for those parameters that we need for the model, training the data, and then executing it. But often one of the first things we do is we prepare our data for use. And if I go down to the second cell, I think Jason's already there. And we can see details like at the top, import pandas. Now, pandas is quite a common library in Python, right, Jason?
It is very, very common for people doing data analysis or data science work. Yes.
So we're using that library there as well. Underneath that, we've got some references to some web libraries, a graphing library, and we've also got a CSV file that we're not using just yet. We'll use a little bit later in the next couple of exercises. But underneath that, we have some data that represents the boot size and the harness sizes of really information that we know that's accurate already. So we've got the boot sizes and their correlating harness sizes. So we're going to use that data to actually train the information as we go through. Underneath that, we're using the Pandas library to load a data frame, which is really its representation of data, so it can work with it nice and efficiently, and then we'll just print out that data set. So Jason, why don't you go ahead and run that cell?
Yeah, while I do that, let me go ahead and augment what you mentioned about Pandas. So Pandas is a library that lets us in our Python code sort of treat our data the way we would in Excel or in say a relational database. That is, allows us to have a two-dimensional model like a table or like an Excel spreadsheet, and then it allows us to do joins amongst those two-dimensional models or do filtering, aggregations, things like that. And in fact, Pandas stands for panel data, because you can imagine a panel of data like an Excel spreadsheet. And so it lets us work with the data like that, but in Python, so that we can then, after doing all those Excel-like transformations, we can then pipe it right into our machine learning code.
Cool. So you've gone ahead and executed that. If we scroll down, we can actually see the output of that execution while it's running. And then a little bit below that, if you scroll down, you should be able to see the data cells. And there should be 50 records there, starting at index 0. So it should go up to 49. And then we can see all the data there. And sometimes it's a good idea to just look at the shape of the data that you're working with, just to get a sense of what's going on. We'll look at that a little bit more. Now, below that, we're going through the process of selecting a model, and the linear regression mechanism that Jason was talking about before is the one we're using here. And in fact, we're importing a library here, the stats model formula.api, and then we're also specifying a formula where the boot size is dependent on the harness size. And then once we've got that formula there, then we're creating the model. And that might look a little bit cryptic, but what we're really saying is we want to create an ordinary least squares model. That's that OLS. And that's that linear regression trend line we're looking for. And we're passing in the formula as well as the data that we want to use in order to train that.
And this is all going to come together once we run this cell and the next couple, and we get that visualization. You're all going to start to go aha with what we were talking about with trend lines and linear regressions, and this is all going to come together. We're 2 button presses away from the if I remember correctly.
And that's a really important thing too as well. Looking at the data and actually looking at it visually, if you can, it gives you a really good sense of what the data is doing. All right, so we've got that. So let's execute that if we haven't already. Yeah. And then we'll go through the process of training it. So we have everything set up, but we haven't done that last step of training the data in order to create the model. So in this point here, we're putting another library called graphing that'll actually do the work of visualizing this information for us. And then
we don't need yet. That come to think of it, we actually use it down here, but whoops.
That's all right. So we're training the model. That model called fit. That's the process for training. And that will actually look at the data, look at the analysis, and try and work out what the parameter values are in order to display. And once you execute that, if you go ahead and click on that, Jason.
So let me recap what you just said while that executes too. We started above in that previous cell. We selected the model that we wanted to use, which was essentially the same one that we had on our PowerPoint, right? It was the one that basically just had one multiplier and then add another term. So we multiply by a term and then we add by a term. And that's essentially it in this case. We are now saying, all right, we picked that model. Then when we come down here and say fit, we're saying use our data to select the optimum multiplying term and addition term. Now, by the way, we did actually, when we selected the model up here, we also gave it the data. We told it which data we're going to train with. We just didn't actually do the training step yet. When we say fit, we do that training step. We say find the optimum parameters. And there they are, by the way.
Awesome. So then we can actually use those parameters and actually let's run the next cell. The next cell is really just going to take the scatter plot. Oh, cool, you've executed already. So it's got that trend line going up, and also it's got the various data points. But what I can see, Jason, is that the dots aren't on the trend line. Shouldn't they be perfect and exactly on the trend line?
This is exactly like we talked about, right? Is we've gotten the least wrong fit, which is exactly what we want to do. There's no such thing as a exactly correct fit. And in fact, if we somehow created a line that went squiggly all over the place with our historic data, we'd find that actually it didn't do very well with the new data anyway, because the real trend is that it looks like this line, but with some variance. That is actually the trend. The variance is part of the trend. So this actually is a very good model for that data.
And it's that least incorrect model, right? That trend line of going up. That's good.
Exactly. Yep. And so, yeah, we can see this is all our historic data that we loaded early on and said, okay, fit a trend line, a predictor to this. And what we get to do now in the future is when we have a harness size, we can come along this spot here and then go, okay, what's the matching boot size?
And in fact, that's what we do. That's what we do on the next step. We're actually going to take that harness size and go, what's going to be the boot size for this particular value? So yeah, we've got that running cell. So we're populating just some parameters, the harness size here, that's the input. And then we're going to apply that to the model and tell us to predict the value of the approximate boot size. So the predict is probably a good term because it's not actually getting it right, but it's saying this is what we think based on the data we've analyzed.
Yeah, I always wished that the jargon in ML was guess, because predict almost sounds like there's like a time element, a future element to it, and that's only sometimes the case. Yeah. Sometimes we're predicting what happens in the future. Sometimes we're guessing what the boot size is. But like you said, it's better than saying give correct answer.
Yeah, I don't want to call that method educated guess. Yeah, absolutely.
I'm not sure what you said. That undersea cable got me on the audio.
That's all right. So we've got that prediction that's coming through. We've got the value that's being displayed here. So if we correlate those values to the graph from before, so we've got the harness size of 52.5, and what would we get typically for the trend line? What's that showing, Jason?
Well, if I go to 52.5, and that's just about right here, that brings me to just about 36.5 on the boot size. And
which matches the output, right? If I'm not mistaken.
Yay.
Awesome. So that's a pretty simple case where we've actually just trained out our first model and taken you through some of the steps that you would do to do a very simple analysis with the ordinary least squares, which is still an effective model. And like you said before, Jason, it's actually used quite a lot in the real world.
Yep. Yes, this is absolutely a real world useful algorithm. Now, more often than not, we'll see it with more inputs than just one. But nonetheless, the rest of the algorithm stays the same. And in fact, we're going to see it with more than one input in that episode 3 or episode 4 when we talk about regression models.
Awesome.
Let's get back to our slides then.
And feel free to send messages through on the chat as well. More than happy to answer questions that come through. Maybe our moderators are just answering all of them for us, Jason.
That is likely. They are a really impressive group of moderators today, I have to say. So they are definitely more than capable of answering the same questions that we are. Although it's fun for us to occasionally answer a question. All right, so we're talking about the inputs and outputs of our parameters. And we've touched on this a little bit already, but I want to focus in on a few key parts. And one of those is just the jargon again. And man, jargon in machine learning is definitely one of the difficult issues. Probably one of the more difficult issues is just getting around the lingo or the jargon that is used, because we borrow jargon from computer science, from statistics, from pure maths. And of course, it's a couple decade old discipline now, and therefore machine learning just has its own crazy invented terms as well. So there's a lot of different jargon. A lot of it is confusing. It can mean, you can have two words that mean the same thing because they came from different places. Two people published papers using different terms for the same concept, and now who knows which one we should use. It's a little challenging. So So one of those pieces of jargon that can be confusing is our input versus our parameter. Now, when we talk about parameters in machine learning, we always are talking about those numbers that we can train. Okay, so when I say those numbers that we can train, I mean these numbers right here. So in the case of our ordinary least squares model, it was that multiplication term and that addition term, which when we put it into our terms of graphing was our slope and our intercept, as we saw earlier. So when we talk about parameters, we're always talking about those numbers that the training process is going to find for us. Parameter is not a synonym for input like we might expect when we're just doing imperative coding, right? With a regular function, the function's input and the function's parameters could be taken to be essentially the same thing. So that's all making sense, right?
Yeah, it is. And I was thinking about that while you're saying that. It's like often because as a developer, you go parameters, well, that's what you supply to something to execute it. But in our case, what we supply in machine learning is data. And then the output is the parameters that we will execute later, right?
Yeah, exactly. So I guess it's probably also not a bad time to bring up, although you know we have a slide to bring it up later, but it's a good time to bring it up in the course of our conversation here, that really our training process is part of our development process. It's not part of our runtime execution. So when we talk about as developers of a function, we would have at runtime, we would supply inputs or parameters to that function and it would execute. And as ML developers, we're going to still supply inputs at runtime to a model, but that model will already be completely trained. At runtime, we have a completely trained and ready to go done model. At development time is when we're going to train the model, and that's when those parameters come into play. So when we're developing, that's where we'll actually do our training process. Later, we'll deploy a model. We do actually have a question here. So we have among various frameworks, Pandas, scikit-learn, PyCharm, Spark, TensorFlow, how do you decide the right framework? That is an excellent question. So a lot of those have slightly different niches. So TensorFlow, PyTorch are used for deep learning, whereas Pandas is just used for slicing and dicing data, usually preparing to go to something like PyTorch or TensorFlow or something like that. And then on the other hand, something like scikit-learn is most often used much the way that we're using that stats model library today for classic machine learning models. Glenn, anything to add to that?
Yes, I think we were talking about before is like not every developer is a Python developer as well. So, for example, you might actually use Python. Oh, actually frozen.
Oh, yeah, I think we've completely kind of lost you there, Glenn. Darn. All right, I'm solo. Here we go. All right, I'm gonna touch on our objective function now while we see if Glenn can unfreeze. So we've talked about training, right? We've talked about that training process. That training process needs something to get better at, right? So we give it a base model and we give it some data, but we're telling it now go get better. Go make those parameters better. What does that mean, make those parameters better? That's our objective function, is the thing that we supply that says, here is during training, we're going to have you keep executing against the data training process until you get better at this function. Now, in our previous example, the objective function, the thing we want to get better at, is just being closer, having that line be closer to the existing data points. And remember, Glenn said the least wrong model. So least wrong in that case is defined as the distances, the total distances between our data points and the trend line being the smallest possible. And so we actually have an objective function that measures that mathematically, measures the distance. And then from there, we can keep getting it better when we don't like it, and we say, oh, that's too much distance, or that's not a very good model. Let's see if we can get it better. That's our training process. And actually, let me just jump over this slide here real quick and continue talking about the training process since I kind of got there. The optimizer is the other key piece of our training process. So the optimizer is the thing that it's the workhorse. It's the heart and soul of the machine learning process. Whereas the model is the thing that we will ultimately deploy, the optimizer is the thing that has kind of the master for loop that goes through during our training process and keeps improving our parameters until they have gotten good at meeting our objective function. So the optimizer is the thing that does that. So that's kind of that master for loop in our training process, or you could even call in some ways you could simply call the optimizer the trainer, the training process. Glenn, are you back with us?
Well, it seems like I am. Can you hear me okay, Jason?
I can, yes. Wonderful.
All right. It's good to be back.
Do you have anything to add to anything I've said over the last few minutes?
No, I think that's all quite relevant. I like to think of the optimizer as like the superhero of the whole process. It does the work and generates the least wrong, or the most accurate representation of what those parameters should be.
That's not a superhero for the modern era. A superhero that does the least wrong thing, I don't know what is. All right, so back to my data slide here. So our data is what we've talked about a lot already, but I want to highlight one more thing on this slide, and that is that during our training process, our data has both the inputs and the outputs. Remember, our historic data, we needed to know what the boot size was so that we could determine when we were least wrong or most wrong or very wrong, right? We could only know if we were wrong if we had the answer, if our guessing was wrong, if we had what the right answer was. And so during the training process, we do need both the inputs and outputs of our historic data. Now, later, we'll be deploying our model. When we deploy that working model to production somewhere, that working model will only get the inputs. So we'll only be giving it harness sizes in our example. And we're kind of then at the mercy of trusting our model to do a good job to predict the outputs. Now, we're not maybe entirely at the model's mercy, because of course we can continue to monitor things and we can do reporting and we can continue to improve our model and all that good stuff. But to some extent, we are, once we publish that model, we are setting it free. Does that sound right to you, sir?
It does. I think probably what we want to do is actually look at this in a bit more depth. We've got a demonstration coming up as well. So let's actually,
yes, sir.
I might actually get you to share your screen, Jason, as well.
All right.
The demo slide, if that's okay.
We'll keep the risk level low.
Yeah.
Excellent. So yeah, I think we're mostly going to be playing with that data this time, kind of doing a very lightweight version of the data cleansing and data preparation process that we'll really dive deep into in our module 3, right?
Yeah, that's right. And it's quite common. Often, because we're working with data, we want to make sure it's got the right shape, that there's no real structural issues to the data. And also you want to do things like see the shape of the data, visualize the data as well as you're working with it. So if we just scroll up to the top, excellent. We actually
do have an interesting question as well. Let me let me see if we can talk about that real quick. Do we have a mapping between what ML model solves what problems? There are definitely some basic mappings out there, and some things that I guess I don't have one right at hand to show you in the presentation deck, but even Microsoft has some published materials on this. But there are a lot of models out in the world, and a lot of variations of models. So during the course of this course, so over the next 9 episodes, we'll talk about several of the common types of problems, like classification, like regression, and we'll talk about the common models that can help with those. But in terms of the laundry lists of hundreds of thousands of, or hundreds and thousands, I guess, of model architectures that exist out there, it changes all the time. So we'll leave it to the good folks at Bing to help us.
Well, there's a couple of things to mention there too as well, Jason. One is we have a session on architectures a little bit later. We'll cover some of that material, not all. Like you said, there's a huge amount. But I'd also recommend people go to microsoft.com/learn, and there's a range of other learning modules as well on machine learning, not just the series that we're doing, but there's a series on things like TensorFlow, for example. You could step through and learn some of that framework, learn how to do things like identify objects from images, etc. Lots of great stuff there, but yeah, explore if you can. Microsoft Learn.
Awesome point. Yes. Hey, do you want to get us started on this lab now then, for real?
Yeah, let's do it. All right. So we're loading the data with Panda. This time we're actually looking at the CSV file, which is, I believe, that second link in the chat window there. And then we're reading that CSV file, the doggy boot harness data in. So even if you could actually just copy that URL and paste it in another tab in the browser and actually see the output there. Cool.
There we are.
So you can see it's got the appropriate shape there of what we're looking at. Now, if we go back and run the cell,
which I did.
Excellent. So we can see that we've got the data there. We can see just the definition or the shape of the data. So the head method will only display the first 5 rows, and that's actually often all we need. We want to look at the structure of the data so we can manipulate it. And in this case, we've got things like the boot size, the harness size, the gender, and the age and years. And it might be that we have columns that are just completely useless to us as well with the model. If we had something like the owner's phone number, that's not going to have any influence with the boot size whatsoever. So we want to do something like delete those columns. And we might find, or we might have domain knowledge that the gender and the age and years has no effect on the boot size as well. So we might want to choose to remove those columns or edit them in some way a little bit later. So if we scroll down, one of the other operations that we often do is we want to filter the data and essentially get the range of data that we know that works. We might have some data outside that range that we know is kind of a little bit too outside the realms of working correctly. So in this case here, actually,
let me actually, since we're a little out of sync, I think. So I want to actually just jump in, and once again, I'll blame that undersea cable. But I wanted to jump in and talk about why would we maybe remove, the sex, gender, or the age of the dog, because it seems like there's maybe like a fair chance that would actually be related to the relationship of the harness and the boot size, right? How the harness and boot correlate. It seems like maybe they're related. But
if you go back to statistics, Jason, as well, it might be that they have a correlation, but they may not be significant either. So you have that effect as well. So one of the things is that the people who design this might have some domain knowledge and know that, well, actually gender doesn't play a role in that boot size relationship as well. So that there is that little bit of mix, but we're using data. But often in this case, the impact it might have might be just irrelevant.
Yeah, or it could be that we've done some data analysis too and realized that there's some null values, and then there's so many null values that we don't think we can clean it up, or just kind of hand wave around it, or values that seem completely wrong, like the age in years. We have 150 on a bunch of our records, so we know the dogs aren't that old. So we know something is amiss. So we decide, you know what? Instead of trying to account for that, instead of maybe being wrong in accounting for it, let's remove that from our data. Yeah.
Yeah. So someone's put in doggy years instead of normal years. That's what you're saying.
Yeah, right. That's actually, Yeah, that's actually something that you could really imagine happening is people putting in the translated the doggy ears. Yeah, exactly.
Cool. So we go back to those columns, those are deleted, and it's also listing the available columns afterwards as well. That was from the cell before.
Oh yeah, and then we did the head and tail here. Once
Yeah.
again, so head we talked about before, and
Which is really useful as well, because when you're often working in real situations, you've got millions of data rows. You don't really want to scroll through a million rows as you're working with the data, and it's going to chew up your memory as well on your machine. So the head and tail are very useful just to look at the shape of that data. Now below that, we also want to filter logically on that data. So for example, maybe we want to look at the data for those dogs that have a harness size less than 55. That's what we're looking at here. We've got a few operations. We're showing the number of rows in total, so we can compare that to the filter a little bit later. And then we've got is small. So the is small is like a binary mask, right, of the data. So we're saying we want to look at we want to create a Boolean column, yeah, where the harness size is less than 55.
Yep, and then yes, and exactly, and then that Boolean column right there that we see here actually gets used as a filter to give us a subset of the small dog data only, and that's down here somewhere. There it is.
Awesome. And then below that, we're showing the number of rows just to compare or just to look at it for our own representation. Awesome. And that looks like a lot of code as well. But just below that, we've got a more simplified version of that code where we're taking the.
Yeah, and let's once again just drill in why would we do this filtering? And again, I think the thing that I just want to keep hammering home is why did we do this filtering? Probably because there was some domain knowledge. When doing machine learning, when doing data analysis, data preparation, you must understand your data. Data is not just data. Data has context. Data has a history. It came from someplace, and if a harness size doesn't have an available size of below 55, if that perhaps is the smallest size that's available, then we have some data problems in all of the other rows. Or maybe we know that below 55, we're into puppy sizes, and puppy sizes behave entirely differently, so we need a different model. But again, it's going to, whatever the reason that we did this, it's going to come down to some kind of our domain knowledge about this data and about doggy harnesses.
Yeah, very good point. Awesome. So we've got the structure just a little bit below that, where we're simplifying the data into just a single line of code. We're getting the smaller paws, we're passing in the expression, the boot size is less than 40, and we're copying that as well, and then showing the last 5 rows of that data.
Yeah, so just another filter operation. Yeah.
Yeah, but this is really the daily fundamentals of working with the data as well. Things like deleting the columns, filtering it, and making sure we've got a clean data to go into the model. Because if you put rubbish into a model, you'll actually have rubbish parameters too, and you want to avoid that as much as you can.
Yeah, and remember, yeah, rubbish isn't just defined. I know I'm going to keep hammering it home. I'm gonna. Rubbish isn't just defined by it not, somehow finding math that works or somehow running into an error or an exception. Rubbish is going to be defined by not getting satisfying predictions, and that can be tricky to know. Did I get as good a prediction as I wanted, or as I could have gotten, or was my model handicapped? Was my model held back by some poor job of data prep? And the only way to know that is to do a good and thorough job of data prep.
Yeah, and we'll actually look at verifying a little bit later in the series too. Awesome. So we've got the chart now of that smaller paws data set, and you can see that visually on the screen. And we've just got that limit, so we can see that the harness size is appropriately filtered, or the boot size is appropriately filtered. Awesome.
And you can almost imagine that trend line going through here again. Of course, now all we've done is to actually plot the data points, but you can visualize it. You can sort of sit here, since we're lucky enough to still only have one input and one output. For now, we can have a nice 2-dimensional graph, and we can see right where that line roughly would go.
Right, exactly. And in fact, you can imagine if you've got a smaller data set, the actual trend line, those two parameters would be slightly different with less data as well.
Yeah, exactly.
Right. So below that, we're also going to do something else that's quite common. And like Jason, I know you're in the US, I'm in Australia, so you use empirical, I use metric. Sometimes we can't communicate with numbers and things like temperatures all the time, but we've got the same situation going on here with our doggies. And some of the harness sizes we have are empirical. We might actually have some in metric in some other form. And part of that data processing is probably making something a little bit more consistent. So here we've got a formula for working out the imperial size based on the metric size that's there, for example. And we might use that because we might have formulas that work with one or the other. I know that when I'm working with things like temperatures and distances, for example, I've got formulas that work for metric and some that work for imperial, and I want to switch those around. So this is a good example of that as well.
Yeah, and the point I was going to make is that while if we look at this, all we're actually doing with this is dividing by a number, which is not likely to actually dramatically affect the performance of our model, because our model multiplies by a number and it finds that number anyway. It would just find a different model or a different parameter that was 2.54 higher. So it's not going to help the model by doing this. What it's going to help is us in our further data analysis. So if what I'm used to seeing is the imperial number, if that is what I'm used to seeing and charting, then I want it that way so that I can do my data analysis in a context that me as the doggy harness expert, I see the context that I'm used to. The other possibility is just that we're normalizing this. If we had a more complicated data set, maybe there was another field that said imperial, or it was just a lookup field that said, okay, is it imperial or is it metric? And then the actual value field we have to adjust based on that. So there's all kinds of weirdnesses like that. But I thought I would call out, and for those of you who may have been noticing, hey, that's just division, which is multiplication, and we already have a multiplication parameter. You're right, but this does help the data analysis part, which is super important, especially when we're otherwise using a relatively simple model like we are. We need to get that data rock solid.
Awesome. Cool. And that's what all we're looking at in this second exercise. So looking at things like the data, working with the Pandas library to get it into the data frame, then start working and manipulating columns, doing things like deleting it, filtering on columns, removing rows of data as well, and then just graphing it to make sure you visualize that data. That's so helpful when you're working with data, to visualize it, both the shape in table form and also visually with charts. I think it's probably time to move back to our slide deck as well, Jason.
Absolutely. So what we've got is a trained model. We actually worked on that in our very first exercise. We created a model, and we can use that model once we've trained it. We can deploy it to the real world and do some work with it and treat it as a function. We can give it more doggy harness sizes and expect doggy boot sizes to come back out. And because we trained it with our real historical data, we can make some assumptions that it should be relatively accurate. However, things change. Maybe our doggy harnesses supplier changed and the harnesses are slightly different sizes, or maybe an upstream supplier changed and so the leather stretches more. There's just an infinite number of reasons that our data starts to become less representational over time. And plus, we're also collecting new data over time. And so we're collecting new data. That means we have a better chance to fit a better model. And so while, yes, we are going to start with a blank model when we very, very, very first start going down the path of needing to create a machine learning model for a business problem, we'll start with blank, we'll train it with the data we have, and then we can use that, assuming that we find it to be good enough. And then we can use that. But then we're going to have an iterative process as we get better data, as we realize that we have the opportunity to create better models, maybe just because we're doing ongoing data analysis, even while our good enough model was in production. We realize we have the opportunity to improve it. And so we will have that development process. Remember that training is a development process. It's developer time. And just like developing new code, you can be doing that work while your current code is in production. You can still be working on the next version. And so we can be training different candidate models, trying to find one that beats the one that we've got in production with new data or with just better ideas or better data cleansing, and then publish that new model as we see here.
So I can imagine in our situation, Jason, that as the rescue harness shop business continues on, maybe if they don't get returns from the customers, they will assume that the harness size and boot size are related, and then use that new data and push that back for more training a little bit later too.
Absolutely. Yes. Yes, absolutely. And then we just keep getting better over time, right? We just keep getting better.
Right.
Once we've trained, of course, we've talked about this before, but let's go ahead and hit it again while we've got a table or a slide that wants to tell us, because it's good information. Once we've trained, we don't need the historic data anymore, right? We train that model, and then that model, which was essentially the framework of some mathematical equations, plus the parameters that help complete what that equation should be. So we've got our candidate model, or our model architecture rather, plus the parameters that give us a complete model. That is all we need to deploy. The old data that we trained with and any other, ancillary preparation code that helped to clean the training data before we trained the model, we don't need any of that. We just need that model, and we can deploy that to production. And in some cases, we can even deploy it to other platforms. So we have systems, right, Glenn, that will allow us to train a model in Python, but in some cases deploy it to environments for Java or environments for .NET, things like that.
Yeah, exactly. And I often like to use Python as well to build my models, and then I'll use something like ML.NET, for example, to execute those models in my desktop applications. So you've got plenty of options as well, and there's lots of good existing standards. You mentioned a standard in one of our earlier conversations, Jason.
Onyx, probably. Yeah, the Onyx
was.
I'm actually built into Windows. Yeah, built into Windows, and it's a thing that ML.NET uses under the hood when it uses a PyTorch model, for instance. Yeah.
Cool. So you've got that ability to move everywhere as well. So develop your model where you like it and transfer it to where you need to go as well. And there's even models for mobile apps as well.
Transfer it to places that are supported. It's not quite universal universal portability, but there's at least some portability. With that, we actually are up on another demo. That means more code, more hands-on, more visuals. I like it.
All right, so let's switch over to the last exercise, where we're just going to use this machine learning model in a more realistic-like scenario. We're going to kind of emulate what the doggy harness business would do if it had some real data and had a new sale coming in, and what that user experience might be. Well, we're using a console app for this, but you can imagine that this would be very similar code to what you might have on a website as well. So we want to do a few things. We want to train the process, and we also want to save it to disk, and we want to load it from disk. Saving to disk and loading from disk doesn't sound too complicated, but it's actually really important when you remember that the training process might go through millions of rows. You don't want to have to train the data every time you actually want to execute the model. So once we've trained the data and we have the parameters, we want to save those parameters to disk. So when we're executing the website, we want to then load the parameters from disk, because then we've just got the values that we need, those parameters. And then we can use that to predict, in our case, what the boot size should be based on the harness size. And then once we have those results, then we can inform the user of what to expect.
Yeah, we can almost... You are having problems with the cable again there.
A little bit.
But yeah, to your point, Glenn, the notebook can almost be viewed as two sections, because we do have a starting section where we once again prep data, train the model, do that stuff that we've done before. But we have a second section to this notebook that you can almost imagine is more like our deploy it, our runtime, our things are happening in the real world now section. And those two sections are separated by saving that file. Because when we save that file and when we then later reload that file, even though in our notebook those two cells are right next to each other, they could be months apart. They could be on different computers, right? All those things. It's just a file at that point. That model is just a file. And so we got it trained. It's done. We don't need the data. We don't need the old library that trained it and all that other stuff.
Yeah, that's exactly right. Once you've actually trained the data, you just need the parameters, and you can work with the model there. All right, so our first step is actually very similar to what we've done in previous steps, where we've actually just read the data from the boot harness CSV file, and we're displaying the head of the structure just to get a shape of it. Below that, that's where we go ahead and train the model. This is very similar to what we had before, but it's actually just done in a single line of code. This time, we're using the ordinary least squares, that linear regression model, saying that the boot size is dependent on the harness size, and then actually it's calling the fit method at the end of that in order to do the training, and then saying that the data is trained. And I can see you've executed that as well, Jason. So all the stuff that we've gone through before. But the next step there, where we're saving and loading a model, this is where we're actually saving it to disk. So our Azure Sandbox that we're running at the moment, we're storing that in the Avalanche dog boot model PKL file, and then we're calling the dump, which is really the save method, where we're saving that model and passing in the file name, and then just printing out that the data is saved. And at that point, we have the model, and we can actually use that in an execution environment as well.
Yeah, so this is the part where I was saying, like, we save the file. That file could then be sent over to a remote server somewhere to do some remote things to run the model remotely without having any connection to our development environment, to our training environment whatsoever.
Right, exactly. So once we've got that file, we can work with it as we need. In our case here, we're just going to load the model in there as well and display the parameters. And the reason we're displaying the parameters is just to show that the model, we have access to that model information. In our case here, we've got a couple of values. We've got the intercept and the harness size. So the intercept, if you remember back to maths, that's where it would intercept the x-axis at point 0. So it would be 5.719, etc. at that point, and then every increment of harness size would actually go up by 0.585. So that's the slope of the line.
Glenn's video
overall.
is kind of frozen, but he was showing us a graph with his arm right there.
Yeah, that's right.
This graph.
Oh my goodness, these overseas cables. We've got to replace the string, I think.
So
all right.
Let's talk. Right, we talked before about how with our simple model here, we're training the intercept, like you said. That's where it's going to intercept kind of the origin point. But we also have the slope, so like this. But that's not what those say. That says intercept and harness size. And the reason for that is because that is the slope of the harness size dimension. So again, if we imagine those parameters being laid out in a chart, in an XY chart, then we can imagine that we're talking about the slope that matches harness size. And if we had many more parameters, we'd have a third dimension, a fourth dimension. Things get really hard to actually imagine in your head once you get beyond 3 dimensions. But the point is there's slopes in all those dimensions, but that plane or superplane, hyperplane still is going to intercept the doggy boot axis at some point, and that still gets to be called the intercept.
Excellent.
That'll be a lot easier to picture in your head, what I just said, once we get into the multiple parameters for our regressions, which once again, more teasers for episode 4.
Right, but now it's time to actually put it into a little bit of practice and then actually show what it might be like, or the experience might be like when we're working with the website for our little doggy boot store and harness store. So just below that, we've got a Python method here, load model and predict. If we just scroll down there, Jason. And this is actually a single method where we'll actually use that model that's been saved to disk. So this method will pass in the harness size, and then we'll look at the details. So we'll load the model from that file
Right.
name that we've already got defined, and then we'll populate the parameters. So the parameters here will really be the harness size. We'll specify the inputs. The harness size will come from the one that's passed to the method, and then we'll call the predict method in order to get what we expect that boot size to be, and then return that boot size. So this method it's called load, model, and predict, but it's basically saying get the boot size that you suggest based on the harness size. And then
Yeah,
below that.
and so yeah, so exactly what you're saying. It's really good to remember that at this point we're done with training data. It's done. We're finished with training data. We're finished with deciding what our intercept, our slope is. All that stuff is done. This is essentially a unit test. And so what we're passing in here is one number. That's one number, not a record, not data, not one with an answer. This is one single number, a harness size, and we're getting out one answer. Right?
Yeah.
So it's just now we've just got this function predict that's doing work for us and not using the historic data anymore, et cetera.
Yeah, I like the fact as well. If we had to train the model every time, there's so much data to work with. But when we're executing it, it's really one multiplication and an addition. It's actually super quick. So that's one of the nice things about running the models after you've gone through the training.
Notice though that we're asking for doggy boot sizes of 32.08575. Boy, I don't know if we sell dog boots in that size.
No, but I imagine it would probably round up a little bit as of that, and you'd want to expect that, and the rounding might be to a whole number for doggies. Like if it was humans, it would be to 0.5, for example, increments for shoe size.
And we actually handle that, right?
Yeah, we do some rounding of the data here in the method below. So this is kind of like a user experience that someone might have, where we're basically calling check size of boots. We pass in the harness size and the boot size, and we go through that process of using that method to check what the boot size would be based on the harness size. So that's that load, model, and predict. And then we then round the boot size that we get back. And then if the selected boot size matches the estimated boot size, then we're in a good position. And we go and inform the customer. Let's just say
Great choice.
Yes, we think those boots will fit. If it's less than the boot size or if it's larger than the boot size, then we give them a warning about the fact that we think that the selection is not the best fit for you, and would suggest you get a particular size, and we output that size as well. And the last line of that method is the check size of boots, passing in the harness size of 55 and the boot size of 39. So if we go ahead and run that cell, I think you may have already done that as well, then we can see that with the harness size of 55, then that's probably too big for the dog at that particular size, and we recommend a doggy boot size of 38. So that's some really useful value of using data that we already have to suggest to customers that they may be buying an inappropriate choice. And that saves a bunch of time for the customers. They don't have to do a return, especially if we're posting it to them. And likewise for us, we don't have to support the customer as much. And it saves us time and money in that process as well. It's a win-win on both sides, and a good, effective demonstration of a very simple machine learning model.
Yeah, and quite frankly, even though this is a relatively simple model under the hood, you know, the one multiplier and then the one addition, you can actually kind of easily imagine someone taking this class right now, this course right now, and then going back to their mom and pop shop, or maybe even bigger than that, and opening up a Jupyter notebook and just kind of having it at the side all the time to help their customers. Now, not everybody has to be an enterprise and has to have a team of hundreds of data scientists doing things with crazy complicated algorithms. You can adapt this to your store that you have, your corner store, and start helping your customers today just by having a Jupyter notebook. You don't need to publish it to a website. This is absolutely something that could be useful in the real world, just as it is.
Awesome. So that was our look at the demo. We looked at a very basic model. We'll look at some other models in later episodes of the series too. We trained the data, we saved the data to disk, we loaded the data back, and then used it to execute something for the customer. Really great stuff.
Yeah, we have a question from Peter. He wants to know, why did we decide to go with linear regression at the beginning? Is there a way to decide what method to follow? This is kind of similar to one of the questions we handled earlier, and in I think probably the real answer is that we're going to address that a lot more in episode 2 and in episode 4. But I will give a quick answer. And linear regression is great for continuous values. And there are other options for continuous values. So I don't want to say like that's the only one, or if it's a continuous value, then you're immediately going to use linear regression. But it's a popular choice, and it's one you're definitely going to want to try and at least see how it works out in most cases. What I mean by continuous values is really what we saw with the doggy boot. We saw that at some point it predicted 37.0847. So that's a numeric value where we can get a value at any point in this numeric range. And we did actually end up rounding it. So we're playing a little fast and loose maybe with the rule of it being continuous. But nonetheless, for numeric values, linear regression is a very good choice. Numeric values where a larger number means a larger number. In other words, even though it's not necessarily having all of the decimals, 37 is smaller than 38, which is smaller than 39. So they're real numbers. They're not tokens or placeholders. That's probably more involved an answer than I really intended to give to that question. The real answer, like I said, is we'll dive deeper in episodes 2 and in episodes 4 on that.
Yeah, it's a really good question. I think for today's episode, it's an introduction series. So we selected one that was very simple and easy to demonstrate, so you can understand the core concepts. But exactly. I think if you wanted a way to decide what method to follow, it's one of those things. The more models you're aware of, the more you can make the appropriate decision. So just like architecture in general, understand as many models as you can. Go, okay, I have this problem. I'm going to apply this particular model. Also, we've also got another question there. How do we safeguard user privacy while allowing machine learning development? That's a great question. Do you want to speak to that, Jason?
I actually am not seeing the question, so would you read that to me again? Oh, here we go.
Sure.
How do we safeguard user privacy while also allowing ML development? Well, that is an extremely complex question. To be honest with you, if you have private data, or even things that can kind of impute private data or imply private data, then you want to be very careful with that. You want to be aware of that. So then at that point, when I say you want to be aware of it, okay, but then what? Sometimes the answer is simply going to be then don't do it. That's actually one very good answer. If you need to rely on private data or on data that is of a protected nature, then sometimes the answer is don't do it. Sometimes the answer is you maybe shouldn't auto approve credit card with no human interaction, or auto decline credit cards with no human interaction, if your model's based on all of this private data and all of this data that's probably somewhat of protected natures. Another way is to simply have a human in the loop. So let the machine learning models do a recommendation, but then have a human in the loop to make sure it makes sense, and use some of the technologies that we have for machine learning models to explain themselves. In other words, justify themselves. They can tell you, oh, I relied on this column, or I relied on that column more than the other ones, and so that can help. But it's a big, long topic of its own.
Yeah, I think there's lots of existing resources for ethical uses of machine learning as well. Even at Microsoft here, we have our own framework as well for those choices that we use. But yeah, that's probably another topic.
And we do have learn modules on responsible AI and on the use of some of the tools that are part of the Azure ML offering.
Cool. All right, Jason, I can see you've got the knowledge check slide on the screen, which is awesome. Hopefully everyone on the call has gone to that link, https://ms/learnlivetv, where you can actually answer the questions that I'm about to ask you, Jason. Are you ready for more questions? And hopefully
I
everyone
think
is as
so.
well.
I'm gonna try to be less wordy. We're actually getting low on time, and plus, man, I've just been really wordy answering these questions, haven't I?
But
I'll
it's been good
I'll
words,
try
Jason.
to
That's fine. All right, question one. Question one, what makes machine learning algorithms different from traditional algorithms? Is it A, machine learning algorithms are always more complicated to build than traditional algorithms? Is it B, machine learning algorithms must be trained every time they're used? Or C, machine learning algorithms are shaped by data directly as part of development, and traditional algorithms are based almost entirely on theory or of opinions of the person writing the code? What do you
Well,
think?
so with A, the idea that machine learning algorithms are always more complicated, it should actually be the opposite. For like. Now, machine learning algorithms can be complicated, don't get me wrong, but for like, if I wanted to classify spam, well, the code, that imperative code that I would have to write, that would be as good at classifying spam as the ML filters are, would be much more complicated. In fact, so much more complicated that I don't know how to write code that's as good as the basic ML models, and neither does anyone else. That's why we're using the ML models instead of the imperative code.
Right.
No, I hit the button. Sorry.
You did. We gave it away. You know what?
I did.
It's not so bad, Jason, because everyone who answered this question in the chat got it right. We've got some smart people on the call.
Fantastic.
Yeah, eight out of eight from the chat, or even
So yes, machine learning algorithms are shaped by the data as part of our development process. Excellent. Machine learning models, do you get tweaked during that development or training process? All right.
Cool. Let's move on to question two then. Question two, when do we want to perform training? Is it A, when we want to use the model, B, only when we want to improve the model, or C, every time we load a model from file? I think we've covered this a few times, but let's drill through the answers. Jason?
All right. So is it whenever we want to use a model, will we do training? And the answer is no, because again, training can be fairly expensive. We want to use the model, which kind of acts as a simple heuristic for this real world situation we're modeling. So it's definitely not whenever we're using it. Let me skip B and go, is it every time we load a model from a file? Well, no, because again, we're loading the model from the file in order to use it. So we're not going to have to retrain it every time. We trained it and then we saved it to file. So that process of elimination tells us that we're going to train the model whenever we want to improve it. Now, the most obvious time when we want to improve our model is when it's brand new and we just opened up our brand new development environment or Jupyter notebook and we said, all right, we're starting from scratch. Obviously, that's a model that's going to need to be improved, but we might need to improve it later as we go on as well.
All right. So looking at the results, most people got this right, actually. So
yeah, mostly not quite everyone. That's good. That means nobody's cheating. That's nice to know. We know if we get a couple wrong answers that it's all real.
That's all right, but this is part of the training process for them as well, that they'll learn that it's actually only when we want to improve the model, right?
And that's right. By the way, it's expected. We need better questions if we have everyone getting all of them correct. That's not. We should not be expecting everyone to get all of them correct. We want these questions to be a bit challenging.
We do. All right, moving on to the third and final question for today. What's the relationship between a model, an objective, and training data? Is it A, the training data is used to make changes to the model? These changes help the model get better at achieving the objective. Is it B, the training data is used to make changes to the objective? These changes help the objective be more like the model. Or is it C, the model is used to make changes to the training data? And these changes help the training data get better at achieving the objective.
So let's take this one in reverse order. So is it that the model is used to make changes to the training data? And here the answer is definitely no. Our training data is actually meant to help us tweak the model, not vice versa. So not that one. Training data is used to make changes to the objective. Well, no, the objective helps us know how good the model is. So we're just using that to see how good the model is. We're not actually going to be changing the objective as we go. So that leaves us with A. The training data is used to make changes to the model. And this is definitely the best answer. In fact, it's really our optimizer that uses data and makes changes to the model and the model's parameters. but this is definitely the best of our answers. And let's see, how did we do in chat? Again, pretty good.
Yeah, most people got that. I think there was an issue with the chat where the third option wasn't available. So, but almost everyone selected the first option, that the training data is used to make changes to the model. But yeah, via the optimizer, like you said. Awesome, wonderful. I think everyone did amazingly well at that. That was great.
Yeah, absolutely. Well done, folks. Well done.
Right, and
that's where we're at.
we're in a very good place. All right, and just to summarize, Jason, do you want to take us through what we've covered today?
Right. So we talked about what do we even do with machine learning? Why are we doing it? Of course, the kind of short answer was we're creating something that's very similar to a function, but can do things that we either don't know how to do with imperative functions, or wouldn't be able to do very efficiently. So it's just another way of getting essentially a function, something that can process our inputs and give us the desired outputs. It's just a special way of doing it. We talked about that special way, which is the training process. Then we talked about how to handle our data so that it can work us through the training process and actually give us the desired outcome. And that
awesome
is today. But today isn't all of it.
There's a lot more to go through, and it's really quite exciting. Like next week, we'll be looking at building classical machine learning models. After that, we've got really a great range of sessions as well, looking at the data for machine learning, training, regression models. There's other concepts as well, like architecture and ROC, and a few others as well. And in fact, there's a question on the chat window I really like. Someone's asked, I have no experience in data science, but would like to grow into it. Can you suggest some next steps of getting certified after I finish this awesome series of Learn Live? Thank you. Well, obviously going through this is one of the fundamentals of this, but also with all the certifications for Microsoft, for example, you can actually go to the certification page and it will show you the suggested Learn training that you should go to for a certification as well. Hopefully one of our moderators can paste one in that's probably appropriate as well. Jason, do you want to speak to that?
Yeah, actually, let me go ahead and flip to the next slide, because what I want to do is when you go to our page for this particular module, you will find yourself as in a learning path. In fact, I think you can even just do aka.ms/learnml with nothing else. And I think that'll actually take you to the learning path. And this series is walking through option 2, which is is the most friendly for this format. I'll put it that way. However, option 1 includes 5 additional modules to it that interweave and kind of reinforce the same concepts, but use different libraries, use different techniques, but they work on the same concepts, just kind of building you up and giving you a different perspective. So that's one great way, is just to do the additional modules that are in this overall package. But also search the rest of Learn. We've got some PyTorch content out there. And on episode 2, we've got, as one of our moderators, an amazing cloud advocate, Jen Looper, who has actually, I think one of her team members is actually with us today as well. Yeah, if you can post the deep learning curriculum that is out in GitHub, if we're able to get that, I promise we'll have it for next week, because Jen Looper will be here, and she was kind of the lead of developing that. But yeah, we'll get the link to that. So that's some amazing curriculum that works with some deep learning libraries to do things like computer vision and NLP, and they don't really require the fundamentals that we're doing here to get into it. You can start playing while learning the fundamentals in parallel with us, is one way to do it. So there's a lot of different ways to handle it, because some of the libraries handle a lot of the difficulty for you.
Yeah, that's great. And also one of the acronyms you mentioned, NLP, which is quite popular, which is natural language processing.
Thank you for calling me on that. Yes, I do have a few acronyms that I are so embedded in there that I forget to define.
Awesome.
But you won't let me get away with it.
I'll try not to. All right. So the next slide we've got is actually our Q&A slide. We've got some time, I think, for a few more questions. There's one in there, Jason. What is AutoML and how is it different from what you showed us today?
So AutoML is a really interesting feature. AutoML is or automated machine learning as the feature is properly called, and the long name as it's properly called in our Azure ML offering. It'll actually look for different candidate models for you. And it will do models like linear regression, like we did today. It will use things like random forest, which we'll use in a few episodes. It'll also look at some deep learning models, some of the deep learning models, and it will determine which one it thinks is best. What's interesting is it's like an AutoML does make things more complicated too. So those of you who don't want things to get more complicated, maybe just cover your ears right now. But it's almost like an outer loop. Remember, our main training loop helps us find the parameters for the model that we chose. If you can imagine an outer loop that chooses the model for you, and then the inner loop finds the optimum parameters. AutoML is that outer loop. And Sadiq wants to know, instead of Python library, any thought to use ML.NET instead? So ML.NET isn't entirely a replacement for some of the Python libraries. It can be for some tasks. So if you're a .NET developer and you do want to do linear regression, for example, then yes, you can do all of your work right in ML.NET. ML.NET can also execute some models that were trained in Python. So you could do the training process in Python, export them to a model format that we discussed a little bit earlier called Onyx. And then that Onyx model can be used by ML.NET. Not all the time. There are some limitations, but they're well documented. And then you can, anywhere you can run .NET, you'd be able to execute that library.
Awesome.
And of course, embed it in your .NET code if that's what your application and existing code base is. Then that helps a lot.
Excellent. And I think that's our last question for today as well, Jason. So I think thank you everyone for coming today to today's session. And we hope to see you on the next episodes that we have over the next 9 weeks. Bye for now.
Next week, same time. Bye.